everybody, it's Mrs. Hofferberth. Let's talk about the standard reduction potential. When you have a voltaic cell, you can calculate what's called the cell potential, also known as the electromotive force or EMF. We're going to call it the cell potential. This cell potential has the symbol E subscript cell, and this is the difference in potential energy for electrons between the anode and the cathode as they're flowing. The units we're going to be using here are volts, and 1 volt is defined as 1 joule per coulomb. We can measure using a voltmeter what this cell potential is for any number of combinations of anodes and cathodes, which is great, but it would be really nice to be able to just predict without having to make a measurement. And the last thing someone wants to do is measure every possible combination of anode and cathode. And so what we've done is we've created a table of standard reduction potentials. And what this is the reduction potential relative to the standard hydrogen electrode. And these are under standard conditions. So you have a pressure of 1 atmosphere for any gases, and concentration of any solutions are 1 molar. Now, the standard hydrogen electrode is just a default reduction that we're going to call 0 volts. It's a reference point. It, of course, isn't itself 0 volts, but it is a reference point that everything else can be compared back to. And the standard hydrogen electrode, called the SHE, is shown in the diagram down below here on the left. And so you've got a 1 molar solution of hydrogen ions, so 1 molar solution of acid. You have hydrogen gas being pumped in at a pressure of 1 atmosphere, and then you have a platinum electrode that allows for the electrons that are freed by that electron transfer to be transferred to the wire, to that external circuit, to whatever other cathode is that you're looking at, or anode that you're looking at. So this is our standard reduction potential. This is our reference point. And people have made tables where they've measured the voltage compared to the standard hydrogen electrode for dozens and dozens and probably even hundreds of substances. Here's a small subset of those reduction potentials. You'll notice that some materials have a standard reduction potential that is positive and some that have negative. But all of them are written as the reduction. So even if in a chemical reaction they're actually going to be oxidized, when we write our table of standard reduction potentials, those are written as the reduction process. You will notice that things that have a positive cell voltage are going to be things that will be easier to reduce. And the more positive that cell potential is, the easier it is to do that reduction. Things that have a more negative cell potential, these are going to be much harder to reduce. In fact, if you paired them with the standard hydrogen electrode, since the standard hydrogen electrode is easier to reduce and they are harder to reduce, that reaction would actually flip and they would end up being oxidized. In general, when you're picking 2 materials, 2 different oxidation reduction processes off of this chart, the one that is more positive will be reduced. The one that is less positive will be oxidized. One last thing to note in terms of terminology here, things that have a more positive standard reduction potential, they're easier to reduce. If they're easier to reduce, they're going to cause something else to be oxidized. So these tend to be good oxidizing agents. And things that are harder to reduce, those are easier to oxidize, so they tend to cause other things to be reduced, and so they are good reducing agents. When you come across a chemical reaction or a situation, perhaps, where you've got multiple items and multiple chemical species in your solution or in your reaction mixture, make sure you look at all of them, including solvents like water, because water can get involved in the oxidation reduction process. And you need to find the one that has the most positive reduction potential. That's what's going to be reduced. And the item with the most negative reduction potential, that's the one that's going to be oxidized. And so you may actually not end up with every chemical species present in your solution getting involved in the chemistry. You'll pick the 2 that'll give you the biggest bang for the buck. Okay, so when we want to use these standard reduction potentials, not just to decide what's being oxidized and what's being reduced, but to actually predict a value for that cell voltage, what we're going to do is take the overall chemical reaction, we're going to break it into its half reactions. So for example, the reaction between zinc and copper to make zinc ions and copper metal, we are going to have the reduction be the copper gaining electrons where the zinc is being oxidized. So when you want to get a value, you're going to use your standard reduction potential table. If you look, copper is written on it exactly as it appears in this equation. So the value for the cell potential for that portion, so we call it E naught reduced, is going to be plus 0.34, which is the value off that standard reduction potential table. For the zinc, if you were to look at it, on that table is the reduction potential. We need to flip that because we're reversing this reaction. Instead of being reduced, it's being oxidized. And so you will reverse the sign on the standard reduction potential. So we're going to take a negative of a negative 0.76 volts. So that's a positive. And then you're going to sum these just like you would sum your overall chemical equation. You will sum your value for these potentials to get the overall cell potential of a positive 1.10 volts. For any spontaneous or thermodynamically favorable process, your cell potential will be positive. If you calculate a negative value, then this is not spontaneous. It would be spontaneous in the reverse reaction. So the reverse process would be thermodynamically favorable. Let's take a look at one more example because I have one more important point to make. When you look at a process, here we have an unbalanced oxidation reduction process where aluminum is reacting with silver ions to form aluminum ions and silver. If we write these half reactions, you will notice that we have a different number of electrons in the oxidation process and the reduction process. So if I'm actually going to have a balanced chemical equation, which is of course what has to happen in real life because we cannot break the law of conservation of mass, I'm going to need to multiply this bottom equation by 3 so that there are 3 electrons being transferred. Let's take a look at what this does to our reduction and oxidation potentials and the overall cell potential. For the oxidation process for that aluminum, this is just the opposite of the reduction potential that you find in a standard reduction potential table. And so I'm going to flip the value for the reduction potential. So it was a negative 1.66 volts, now it's going to become positive. For the reduction, if I look at the table, it's for 1. Silver plus 1 electron makes silver metal. But because voltage is a ratio, it's joules per coulomb, by having more electrons transferred, we have more coulombs of charge as well as more energy. And so it is actually an intensive property. You do not multiply. You do not multiply reduction potentials. You just use the value off the table of 0.80 volts, and you add this up to find that your cell potential is a positive 2.46 volts. I repeat, you do not multiply standard reduction potentials by coefficients when you are manipulating equations. You will change the sign if you flip the equation, but don't multiply by any coefficients. It is an intensive property, and so that ratio remains the same. So, in sum, you can talk about and measure a cell potential for an oxidation reduction process, and that's going to give you information about the driving force for your reaction. We'll talk about that very shortly. For any spontaneous process, the cell potential will be positive. If you have a reaction and you'd like to know its cell potential, you can use the table of standard reduction potentials, flipping the sign on the half reaction that's going to be oxidized because you're reversing that process. But if you need to multiply by a coefficient while you're balancing your electrons gained and lost, you do not multiply by any coefficients. Lastly, you can use that standard reduction potential to decide which chemical species will be oxidized and which will be reduced during a chemical reaction. The chemical species with the more positive reduction potential will be reduced. The one with the least positive reduction potential, that one will be oxidized.